So the next question that is asked from the subject transducers in the series 3 for IN branch is from the subtopic resistive transducers. It is for 2 marks. So this is also one of the frequent topics which is asked in GATE papers. So let's go through the question. So it's basically fill in the blank question. So here a particular resistive transducer has a load resistance 2.5 times the potentiometer resistance. So the ratio is given as 2.5 times the potentiometer resistance. So what is the percentage loading error for the slider position corresponding to 50% of the full scale travel of the slider? So here we can interpret the question and we can draw a diagram on what is asked. So we have a potentiometer which is connected to a voltage source Vs, and where the total resistance of the potentiometer I am giving a notation as Rm, and the displacement be Xm, which is the complete displacement of the pot, and here is a load which is connected to the pot where you can see the slider, the arrow here, which can move up and down for the pot, and let's say the displacement of the load is X meters, and the total resistance is R, or this is the resistance R which is connected across it. So it can travel from 0 to max a position here which is Rm. So here the effective resistance, the remaining resistance, is total resistance minus the resistance which is traveled by the slider. So I am representing that as Rm minus R. So here we need to calculate what is the percentage loading error of the slider. So we need to calculate what is the loading when load is not connected, and with load connected then only you can measure the error and you can calculate the percentage. So first we need to calculate when load is not connected, what is the output voltage. So the output voltage is nothing but the supply voltage, which is Vs, times the R by Rm. So which is clearly from network theory concepts we can derive. So as the slider moves up, so you get more voltage, because voltage equal to current into resistance. So more is the resistance, more is the output voltage. So hence we get an output voltage when there is no load connected. We get it as output is equal to the output I am taking from here. So this is my output. So V output is equal to supply voltage times the resistance. So if more is the value of R, more is the movement of the slider up, we get more is the value of R, and we get more output voltage. So from that we can make a relation which is nothing but a linear relation, because it's a resistive type transducers. V output equal to Vs times R by Rm, which is nothing but X by Xm in terms of displacement. So given X by Xm equal to 50% of the full scale, so 50 by 100, if I take Xm as 100%, so it comes as half. So I got a relation now between output voltage and supply voltage, which is V out by Vs equal to R by Rm equal to half, so which is computed from here. So V output is equal to half times Vs. So this is my first quantity with no loading effect. So when I considered a loading effect, here the question is why loading effect comes, because the given load is not an ideal load, and for an ideal load we know from network theory concept that it should have an infinite resistance, input resistance, which is not the case, and it has resistance 2.5 times. So which I go through the question. If I go through the question, the resistance of the load is 2.5 times the potentiometer resistance. So it is not an ideal load. So it has got some resistance inside it, which I am representing as small r. So this small r corresponds to load resistance. So when we consider the loading effect, we get the output expression as output voltage divided by supply voltage is equal to 1 by the total resistance of the pot by total displacement of the pot by the displacement of the slider plus Rm by R into 1 minus X by Xm. So we have calculated X by Xm as 2 from the above expression, plus R is given as 2.5 times the pot resistance. So 2.5 times the pot resistance, and X by Xm is 1 by 2. So on solving for this, we get the ratio of output by input as voltage, which is V out by Vs equal to 5 by 11. So now we have calculated both the quantities with loading and without loading. So when I substitute the quantities to calculate the percentage of loading error, which is with loading minus without loading by without loading, which is 5 by 11 minus from this it is half times Vs. So I take the output quantity V output by Vs as common divided by half, so I get minus 0.909%, which is the loading effect.